Hi everyone, and welcome to another episode of Brainsmatter. Today I've got Jürgen Knödlseder with us today, and he's got an interest in astronomy, especially dealing with gamma rays. Welcome to the show, Jürgen.
Yeah, thank you very much. Thank you for inviting me to have you on your show.
So firstly, could you tell us a little bit about yourself, your background, and what you were interested in school and how you got to where you are today?
Yeah, so in fact, when I was a kid, I was a lot of dreaming about the stars and stargazing, going out with my binoculars, looking at the sky, finding out what different objects are, and so on. So I think this is something which fascinated me since ever. And it relates also to my fascination for nature. I mean, this is, for me, it's part of nature. And looking to nature, observing nature, and trying to understand how it works. I mean, this, I think, always fascinated me. And in school, well, I mean, there were areas of topics where I was better than in others, and topics were like physics and math. So, I mean, it was obvious that I wanted to do some work later in these fields. And then when I came to doing some studies, it was also pretty obvious that I wanted to study physics. So I went to the Technical University in Munich to study general physics, not really specifically astrophysics, but physics in general. But there were astrophysics lectures, which I enjoyed a lot, and they connected pretty much with my fascination that I had for this field when I was a kid. And at some point in time, you know, when you're studying, when I was studying in Germany, I mean, at some point in time, I wanted to earn some money also because, I mean, when you study in Germany, you had quite some long periods without studies, and I wanted to do some traveling. I wanted actually to buy a motorbike at that time. And so somebody told me, as a friend told me, well, this professor, this astrophysics professor there, he looks for students. He has some work for them to do in his lab. He's working on a new project. And so after the lecture, I went to the professor, I asked him, does he have some job in his group? And he actually had. And the project he was working on was a new satellite for gamma ray astronomy. And that's how I slipped into that. It's just because, I mean, by chance, I was this professor working in a given field, and it was an opportunity for me, first of all, to earn some money, but also, I mean, to start to do science in a field.
So could you explain to the viewers and listeners what gamma rays are?
If you look, I mean, the light you capture with your eyes has different colors. And basically goes from red to blue. And what this means is basically that the photons, the light particles behind that, change their energy. Basically, when you go from red to blue, you double the energy. But that's not all the light that exists in the universe. I mean, there's much more light that we just cannot see with our eyes, but it's still there. If you go beyond the red, there's infrared light, there's microwave, there are radio waves. All this is just light, but with lower frequency or with longer wavelength. And also beyond the blue, there's light, there's ultraviolet, there's X-rays, and there's gamma rays. So these are just different kinds of lights we cannot see with our eyes, but that exist with our electromagnetic waves. So gamma rays is just the most energetic form of light that exists. It's just roughly, I mean, gamma rays start with light particles, with photons that have roughly 1,000,000 times the energy of the visible light we capture with our eyes.
Can you tell me a little bit about the project that you worked on with this professor?
Yeah, so this was the so-called Compton Telescope. Compton means Compton Telescope. And this was to explore the sky at MEV energies. So what is MEV energy? So in gamma ray astronomy or high energy astronomy, we often measure the energy of light in a unit called electron volt. And if you have 1,000,000 electron volt, it's MeV. So an electron volt is the energy that an electron gains when it goes through the potential of 1 volt. So typical visual light has 1 electron volt of energy. And so in gamma ray, we start at 1 MeV. So it's the low energy part, if you like, of the gamma rays. And this is in fact a very tough regime because light interacts very little with matter in this regime. The interaction, in fact, the primary interaction mechanism is something is called Compton scattering. So what the light is doing, it meets the matter, specifically electrons, and it's just scattered by these electrons. It will lose some energy. It will give this energy to the electron and then fly in another direction away. It's like playing billiard. Light is coming in and doing something with the electron and moves away in another direction. And what we did with this telescope is basically reconstructing the direction of the white ball in the billiard, the incident gamma ray, from the direction and the speed of the other balls. Basically from the interaction products of this Compton scattering. So this is, you need to be quite clever to do this, and it's really quite challenging. But at the end, it allows to make images of the sky and also to measure spectra, which means how the light intensity changes with energy or with color, if you like.
How long did this particular set of experiments take in measuring all of these gamma rays?
So the satellite was up for 9 years. It was in fact the biggest satellite ever launched for science by NASA. It was the Compton Gamma Ray Observatory. There were 4 telescopes aboard. It was like a bus. It was launched by the space shuttle in 1991. And so it orbited the Earth for 9 years. It was actually deorbited, so it came back to Earth, and somewhere today is on the bottom of the Pacific Ocean. And you need very long exposures, in fact, to measure these gamma rays, because first gamma rays are very rare; they are not very much coming in, and then we have a huge noise, what we call instrumental noise. Because when you put up the satellite, it flies in space, and the space is filled with particles, what we call also the cosmic rays. And these cosmic rays, they bombard everything that is in space, and also our satellite, our telescope. And what these particles make is, at the end, nuclear reactions. And it just happens that the typical energy of these nuclear reactions is about a mega electron volt. Right, the energy where we want to observe our gamma rays. So we have lots of noise, and then we have a few gamma rays among all these different signals. So it's like observing the sky during daytime. It's very hard to see the stars during daytime because the sun is so bright. And that's exactly what happens. We have so much background coming in. It's very hard to see the gamma rays. So you have to observe for a very long time that you can really see anything. And very often that we analyze the data, we analyze basically all the 9 years of data we had at hand at the end.
So effectively what you're doing is looking at that long time period and subtracting the visible light, and what you're left with is the gamma rays. Is that right?
Yeah, well, what you call visible light is our background, so we have to understand our background and at the end model it pretty accurately and then try to subtract this off, and then hopefully what remains is not background or any artifacts, but the real gamma ray sky. And of course we managed to do this, and of course it was quite challenging, and sometimes we had also false alerts and all these kind of things, but we could do quite some exciting science.
So you were doing that while you were still a student, weren't you?
Well, I started to do that, but I also did my PhD then on Comptel, PhD thesis. So I really also started my really scientific career like that.
was your particular PhD topic about in relation to CompTel?
Yes, so I got pretty fascinated or interested in radioactivities. So radioactivities on Earth, you associate them to nuclear reactors, but also in space there are radioactivities. So what's happening is actually, I mean, that the elements that we know today, I mean, the iron, the aluminum, all the elements around us, they are made in stars, actually. And the process through which they are made is called nucleosynthesis, the creation of nuclei, of elements. And this process is still going on. I mean, the sun is currently building helium out of hydrogen. That's nucleosynthesis going on. So in this nucleosynthesis process, you create lots of different elements. And you also create eventually radioactive isotopes, which means these are isotopes that are not stable and that will decay after some time to become a different kind of element. And there are a few radioactive isotopes that you actually can see through gamma rays, because very often when they are made, they are in a very dense object, like in the inner part of the sun, so you cannot see actually the gamma rays because they're just absorbed in the sun. But if you have a long-living radioactive isotope, it can come out of the nuclear reactor in the interstellar medium in our galaxy, and then you can see the gamma rays from the decay of this radioactive isotope. So there was this one isotope which is called aluminum-26. It's like the aluminum in the kitchen, but this one is aluminum-27. So you have to strip of one neutron, making aluminum-26, and then it is radioactive. This means it will decay into magnesium-26 at the end. And when it decays, it will emit a gamma ray of 1.8 mega electron volt. And so it makes a line. It's really a very distinct feature at a given energy. And so we just made an image of the entire sky in this narrow energy window to make a map of the galaxy in the light of radioactive aluminum. And the reason why we wanted to do that is because it was known since the 1980s, basically, that there is such a line somewhere coming from the center of our galaxy. And the problem was, in fact, that there were many different possibilities to make this aluminum-26. It could be massive stars, supernova explosions, but also less massive objects like nova, so white dwarfs on which there are also explosions, or red giant stars that eventually could make aluminum-26. So we wanted basically to sort out who is guilty for producing this galactic radioactivity. And so the aim was to make a map and then compare the distribution of where the aluminum was to the distribution of different objects like massive stars, nova, red giants, and so to find out who is the source of radioactive aluminum.
Did you end up discovering who the culprit was?
At least we could limit it. So we could exclude it's not nowhere. It's not red giant stars. It must be something related to massive stars. So it could be either massive stars when they explode as supernova, or it could be very massive stars, something stars more massive than 20 solar masses, or 20 times the mass of our sun, that expel, in fact, a very strong wind in the interstellar medium. And in this wind, there would be this radioactive aluminum that we see in our data. So we couldn't distinguish between these two scenarios, explosions or winds, but it was obvious from the distribution, it was clearly related to massive stars.
After all of that work that you've done in your PhD, you did move into hardware development, didn't you?
Yeah, in fact, I was doing my PhD study here in Toulouse, so in France, at the lab that is now called IRAP. Institute for Astrophysics and Planetary Science Research. And at this lab at the time, there was ongoing a development of a new gamma ray satellite, new gamma ray telescope put on a new satellite. And was a new MEV satellite, basically, even observing a bit at lower energies than Comptel did. So there was, of course, a lot of hardware developments ongoing at this lab, and this was an excellent opportunity. I just finished my PhD to get involved in space hardware development. So I was in fact responsible for a small box. Well, I didn't build this box, but I had to verify it, and I had to make tests, and I wrote even quite a bunch of software that is working still in this box because the satellite is still working. And it was quite interesting to learn about this. So I spent a lot of time in clean rooms. I spent a lot of time at the ESTEC Center in the Netherlands, where the European Space Agency assembles all the satellites, because it was a European satellite, the Integral satellite, which was launched in 2002. And on this, there was a spectrometer that was built in Toulouse, which was there for making very precise measurements of the energy of the gamma rays. With Comptel, we had some idea of the energy, but the measurement was not very precise. So what I told before, that we measured the gamma ray line, what we've seen was quite broad. Now, this new satellite used germanium as detector, and with germanium, you can make very precise energy measurements, and this gives you access to the kinematics of the particles that are behind the gamma ray emission. This was quite exciting. This new dimension in the observatory space, if you will.
This particular device was also looking at positrons as well, wasn't it?
Yeah, in fact, as I said before, I mean, the speed telescope even looked a bit at lower energies. And there's, in fact, an interesting thing in nature is that every particle has an antiparticle. Antiparticle is basically the same kind of particle, but it has an opposite charge. So an electron has a negative charge, and the antiparticle is a positron with a positive charge. Now, when these two guys meet, something strange really happening, because they disappear and just become light. That's what's called annihilation. So you can create particles out of light. Just if light collides, you can collide light and make particles. And if these particles collide, they make light. And since the 70s, there was an observation of a gamma ray line from the galactic center again at exactly 511 kiloelectron volt. So 511 kiloelectron volt, that's just the mass of the electron. And if you see this line, you're sure that there is some annihilation ongoing. Because if you have an electron 511, a positron 511 keV, they come together and they make, in fact, two gamma rays. It's because of momentum conservation. So two particles making two gamma rays. So these two gamma rays also have 511 keV. So it's a very clear signature of positron annihilation. And so we want to learn, I mean, how are these positrons distributed? And who's the culprit again? I mean, who is making these positrons? Because our universe is just made of matter and not of antimatter. So there must be an engine that creates positrons, or at least has created in the recent past positrons towards the galactic center.
You were also able to show through this work that gamma rays can be focused.
Yeah. Well, I mean, that's what's in fact another experiment, because it's in fact funny. Because you open a textbook, you always read, you cannot focus gamma rays. And to some extent, this is right. So why do you want to focus gamma rays? Well, as I told you, one of the biggest issues in our field is the strong instrumental background. this noise coming from the cosmic rays. Now, to make a more sensitive detector, typically, the detector is just collecting gamma rays, so you make it more sensitive, you need a bigger detector to collect more gamma rays. But if you make a bigger detector, you have also a bigger mass in space, meaning that you create more background, because a bigger mass and more particles coming in, making more background. So in fact, it's very tough to make a better instrument because whatever you do, you make more background. So typically what you do in other fields is you separate the collector from the detector. Like in an optical telescope, you have a huge mirror and a small camera. And so you can have a small detector, little background, but still a huge collector. And we said, well, it's a pity that all the textbooks say it's not possible to do this in gamma rays. And the reason why they say this is that because in fact the wavelength of the gamma ray is so small that it's smaller than the distance between atoms of any matter. And this means that just the gamma ray goes through the matter. It's not reflected by the matter. If you want to be reflected by the matter, your wavelength has to be bigger than the distance of the atoms in the matter. But there's one thing how you can eventually make it work. And that's called Bragg reflection. That's basically when in a crystal, you have planes in a crystal, and you can reflect light. Specifically, this is used in X-ray for X-rays. You can reflect X-rays by the planes in a crystal. Now, the thing is that you basically, the planes, of course, they also have an atomic distance, but you can incline your crystal in a way that you have a kind of grazing incidence. And then effectively, the distance between the planes becomes smaller than the wavelengths of the gamma ray. So you can also deflect, in fact, gamma rays by Bragg reflection in a crystal. And if you take now all these crystals and you put them on a ring and you tune them very precisely, then you can have a kind of collector that will deflect all the gamma rays on a detector. So was not us who invented the idea. It was in fact somebody in the United States who worked on that, but not in the field of astronomy. And once we found this out, we said that, well, let's try it out. And if you want to try something out in our field, you put it on a balloon. A stratospheric balloon, it goes even up higher, 30 to 40 kilometers. It floats basically above the atmosphere. There's very little atmosphere remaining on top of this balloon. And that's why you need this balloon, because gamma rays cannot reach the surface of the Earth. They will be absorbed by the atmosphere. So you have to go above the atmosphere. But if you fly a balloon at 30 to 40 kilometers, you can detect gamma rays. The 511 line we just talked about before was discovered by balloon experiments, and many things were discovered initially by balloon experiments. So we had a project flying a gamma ray lens on a balloon with 2 flights. And in the second flight, this was really a very successful flight. We observed, in fact, the crab, which is the crab is in fact a pulsar and a nebula, pulsar wind nebula, and it's the brightest source we have in gamma rays. And we managed to observe 40 gamma ray photons from the crab with our lens. So we demonstrated that we can really focus the gamma rays through the lens on a small detector and make astronomy with that. Well, this was very exciting. And then we said, okay, now let's make a satellite project. And we made a proposal to the European Space Agency, but unfortunately it didn't went through. And I'm not sure that today anyone is still working on gamma ray lenses for gamma ray astronomy, but it was a very nice and very interesting project and a nice demonstration.
Or maybe someone who's listening or watching this can pick up on some of that gamma ray research later on.
Yeah, definitely. I mean, it's very often like that. I mean, once the idea is around, I mean, even if it's not realized immediately, maybe somebody else will pick it up and develop it further and bring it alive.
Jürgen, thanks for joining us today and talking to us about gamma ray astronomy. I'd love you to come back.
You're welcome.
Thanks for listening to the show. You can check out the brainsmatter website at www.brainsmatter.com, and you can find all the other episodes of the show there. There's also other information on the site, such as guests who've been on the show and subscription details. You can also find brainsmatter on YouTube, so make sure you like and subscribe if you're a YouTube listener. If you want to support the show, please consider becoming a Patreon at patreon.com/brainsmatter and signing up to one of the options there. Or you can donate either once off or regularly via PayPal. All you need to do is click on one of the PayPal donation options on the right-hand side of the website. If you have any comments or suggestions, you can leave an entry on this episode's show notes on the webpage or on YouTube, or you can send me an email. All my contact information can be found on the brainsmatter website. The theme music Soul of the Machine was composed and performed by Clive Weeks and is used with his permission. I hope you enjoyed the show. Bye for now.